or aldehyde, doesn't matter what you use, both will react. If you're using liquid aluminum hydride, it will deliver the hydride, make an alcohol. Soluble hydride, deliver the hydrogen, make an alcohol. They're the same. If it's an aldehyde, same thing. Deliver the hydride, make an alcohol, deliver the hydride, soluble hydride, deliver the hydride, make the same alcohol. So ketone or aldehyde, it doesn't make any differences which hydride you use. But if you have a carboxylic acid, then things change. Soluble hydride, no reaction because it's not powerful enough. Nothing will happen. But the lithium aluminum hydride, it will react multiple times. You eventually get the primary alcohol. If you're wondering why it makes a primary alcohol, I'll tell you a little bit later. If it's an ester, same situation. Ester with the lithium aluminum hydride, you get the primary alcohol. Sodium borohydride, no reaction. So you can see that these will react differently. And that's something we're probably going to have. So let me show you why it makes a primary alcohol from the carboxylic acid or ester. So this is an ester, right? It is actually the same way that as the Grignard reaction, like reacting twice. It actually becomes the exact same mechanisms. You get the carbonyl of the ester, hydride of the lithium aluminum hydride makes an attack, opens it up. You get the alkoxide here. But the problem is you have a leaving groups. So that's the same situation. So you get the carbonyl, made it back, and then by kicking these methoxy groups out, you get an aldehyde. So first hydride reactions, you get an aldehyde, and aldehyde is not safe with the lithium aluminum hydride. Second hydride is going to be delivered, and then now nothing going to leave, everything stuck there until you add the water, you get the alcohol. So you are consuming two hydride, like Grignard reacting twice with an ester, lithium aluminum hydride reacting twice with an ester. So it's kind of the same concept. What about the carboxylic acid? Carboxylic acid actually consumes 3 times. It's a little bit different. First reaction is not the hydride attacking carbonyl. This is acidic hydrogen, you get the basic hydrogen. This is actually where the acid-base reactions. You get the hydrogen gas comes out. It's kind of reacting violently, so you really want to do it in the high speed. But anyway, the first reaction is actually the hydride reacting the proton, make the hydrogen gas, but at the same time, you're actually making an aluminum ester with the carbonyl. So now it becomes like an ester. Now you can see it's going to react one more time. Another hydride makes an attack, make an alkoxide here, but this will come, kick it out, you're going to get an aldehyde again. Third hydride makes an attack to the primary alcohol. So in total, you consume 3 hydride to reduce the carboxylic acid to the alcohol. But you get the primary alcohol. After you consume 2 hydride, you get the ester. That's the reason why you get the same products from both of them. Okay. Well, you may not. You know the mechanism. It makes it better, but it still can't do without the mechanisms. But at least you should figure out this one. You have a molecule having a aldehyde in the one end, ester in the other end. You're going to be having different products depending on what reagent you use. If you're using the lithium aluminum hydride reacting with an aldehyde, make an alkoxide, no problem. But it's also going to react with this ester. It reacts with that, it makes an alkoxide groups. But the problem is, it doesn't stop there. Okay. Carbonyl is going to be made back by kicking the methoxy out, and then you get the aldehyde. Aldehyde is going to be reacting again. Then finally, both of them become alkoxide. Now it doesn't have nothing to live. It gets protonated. So you get both sides as an alcohol. That's what happens. You got that becomes an alcohol, that also becomes an alcohol. If you treat that with a sodium borohydride, only the aldehyde side can react, not the rest of part. So this part remain the same. That part is the one that get reacted. So you get different products. So these are the things that you really have to recognize. Yeah, there are catalytic hydrogenations are possible to reducing not only the double bonds, but also the carbonyl. But this one, hydrogen gas with the vanillin nickel or the platinum will do the job. Platinum does that too. But the thing is that you can imagine that using platinum is actually very expensive. It's very precious metal. If you want to have platinum, you probably want to have it on your finger, not using this. So probably this is not the best way of reducing the carbonyl. So vanillin nickel, as I said, the very porous nickel, that's the one that does the job. If you're treating the hydrogen gas with the vanillin nickel, double bond is reduced, but at the same time, the carbonyl is also getting reduced to level. So this is kind of situation very interesting. We can also do things very selectively. We can reduce all of them, or we can just reduce the double bond, or we can only reduce this carbonyl. We can choose what to do depending on what reagent you use. So let's say one will just reducing a double bond, not reducing the carbonyl. That's the one, it's palladium. Palladiums are more selective to double bonds. Palladiums are not really doing much for the carbonyl. So if you're using a palladiums with a hydrogen gas, you're reducing double bond without touching those carbonyl. If you want to just reducing the carbonyl, not the double bond, then you just know sodium borohydride, lithium hydride, that's the one to use. If you want to reduce all of them at once, yeah, that may be the way to go. Or you can do sequentially. You do this and you do that. No. You have a choice of doing things.